call that roller coaster. I'm going to slow it down a bit, and I'm going to talk about slime and the mathematics of goop. So let me start by straight away asking, what are these fluids? What I mean by goop and other funny fluids. Well, I brought a few examples. I'm sure you've all had, it's been a while since lunch, and maybe some of you are feeling hungry. I'm sure you've all seen pizza. And the important thing in pizza is this stringy cheese. You notice how stringy it is here. And there's other examples of funny foodstuffs, for example, mayonnaise. I'll say a bit about that later. So here's mayonnaise. Bread dough, if anyone's made bread, you'll know that that's rather a strange fluid as you mix it up. Another area is what's called personal care, so things like shampoo or shower gel or sun cream or toothpaste. These are all rather strange fluids that have very unusual properties. And finally, in a sense, where the money is and why most of where I do my research is that if you take plastics and you heat them up, which is after all how you make things like these plastic water bottles, then molten plastics behave very much like pizza cheese. They're rather stringy, they're rather rubber-like, and in fact that's rather important. That's why you can actually blow a bottle like this up, because it's that stringiness that keeps the thing together, otherwise it would simply pop like a balloon. And there's a whole host of other engineering materials as well as molten plastics. There are things like inks. A lot of work I do is to do with inkjet printing, and also drilling muds. When you drill down for oil, you have to get the rock back up. And what they use is they use very special muds, as they call them, which are designed to essentially bring up the rock particles as easily as possible. So those are some of the funny fluids. And what I want to show you is some examples of them. I brought quite a few little demonstrations along just to show you. And I also want to show you a little bit about the mathematics about how you could describe them. So where do we start? Well, first of all, what's an ordinary fluid? What is the properties of water? Or there's another thing here I've got, which is a kind of syrup. So let me just pour these out so you know. I'm sure you haven't seen what water's like. But that's just that I'm thirsty. And this is syrup. This is rather like golden syrup. It's American golden syrup. So it's clear. And you can see that it is quite different. It's very runny. It's rather like honey, this stuff. But those are ordinary Newtonian fluids. And the reason they're called Newtonian fluids is because amongst the many other things that Sir Isaac Newton did was he was the first person to really write down ideas about mathematical expressions for liquids. And what he thought about was an experiment where you take two plates, you put fluid in between them, and then you move the top plate, you slide it over the fluid, and so the fluid has to deform somewhat like that. And what Newton postulated, because I think I'm not sure how many experiments he really did on this, was that if you calculated how much force it took to slide the plate, then that depends on, well, first of all, the area of the plates, and also how fast you're trying to push it and how big the gap is. And if you look at this diagram, you can see what's important is actually the ratio of velocity divided by height. And that's something we call the strain rate or the shear rate. And Newton's postulate was that this force over area should be directly proportional to this strain rate. So if you plotted them on a graph, stress versus strain rate, you get a straight line. And the constant of proportionality that comes in there is what people call the viscosity. So in water, the viscosity is about 1/100 of a Pascal second. And this syrup is much more viscous. It's more like 100 to 1,000 Pascal seconds. So it's 10 to 100,000 times more viscous than the water. So those are ordinary Newtonian fluids, and that applies to quite a lot of materials. Water, syrup. Air is also a fluid with the viscosity. But what I'm interested in this talk is actually other kinds of fluids. So what else can you have if it's not a Newtonian fluid? So what is a non-Newtonian fluid in the jargon? Well, it's just a fluid that isn't Newtonian. So it's not actually a very useful definition. It doesn't tell you anything, it just tells you what it isn't. And clearly there are many different ways in which we can have non-Newtonian behaviour. So let me start with just a fairly simple one, and just think about fluids in this shearing experiment of Newton's, and what sort of other possibilities you could have. Well, clearly you've got stress as a function of strain rate, and in Newtonian fluids it's a straight line, so clearly you can have a curve. So what about, for example, a curve like this? And you can see what happens now, the slope's decreasing as you increase the strain rate, and that's called shear thinning. Basically it means that the fluid's getting thinner as you increase it, as you increase the shear rate. And that's a useful property in things like paint. So when you're painting, of course you want a nice thin fluid so that you get a nice thin smooth layer, a nice thin coating. If you have something that's very viscous like this syrup, it'd be rather hard to get a nice thin uniform layer with it. On the other hand, if you have something as thin as water, then as soon as I paint my vertical wall, it's all going to slide down off the wall. So what you want is something that's much thicker when it's actually on the wall under the rather weak force of gravity, but it's quite thin when you paint it. And so modern paints in particular are designed to essentially follow this sort of curve, in fact something probably a bit more extreme than this. So that's one possibility. What about the opposite behaviour? That's called shear thickening for obvious reasons, and this is a nice example. This is bird's custard powder. You can also use corn flour if you want. And what you do is you don't follow the manufacturer's instructions. So when you make custard out of this, what you do is you add a little bit of custard powder to quite a lot of milk. So what I've done here is I've taken an awful lot of custard powder, pretty much a whole tin, and then I've added a small amount of water. And you get a sort of goopy fluid with rather strange properties. So, does anyone want to have a little go with this? Do you want to have a little feel with it? So if you stir it very slowly, it's actually quite easy to stir it. But if you try and go quickly, it's almost impossible. Thank you. In fact, you can play some quite good games with this. You can actually roll it in a ball. You see, you can actually keep it. As long as I keep moving, it will stay almost solid. As soon as I stop, it won't. And in fact, there you see, it'll pour back into the hole like that. My good friend Oliver's sitting over there. It's his. Do you mind if we get a bit messy? Right. So that's a small amount of that. You might wonder what would happen if you had a very, very large amount of that kind of fluid. And that's where this little video comes in. So this is from YouTube. It's in Spanish, so I don't actually know what's going on.